Okay, so here's where we were last time. We were talking about a new kind of a problem that could be, hopefully, fingers crossed, addressed with a mathematical construction that's kind of like a Riemann sum, right? Or kind of like the Riemann sums that we saw previously, right? So previously, we used Riemann sums in this form, right? And the idea is that you take an interval from A to B and chop it up into little pieces, and that the problem should break down along those lines in the sense that on each piece there's some function that you multiply by the length of the subinterval, and then you add that up over all the pieces. Take a limit for round-off error purposes. Okay, so we want something that's kind of morally along those lines, but what if we have a two-dimensional domain? And so now, as much as I kind of downplay the idea of geometric, thinking of integrals from the point of view of the geometric application, it's really more that I want to downplay thinking of integrals in terms of the geometric applications exclusively, right? Or, foundationally. That's what I think the mistake is. But let's acknowledge that geometric applications are great. I can see the picture, I can see what I'm doing, and it's very relatable. And there is something great about that. So, as a first example, I'm going to go with the geometric application. We're going to look at the volume under this graph. Note here. Color change. This is a graph that we are looking at, and wanting to find the volume under that graph is the question at hand. Okay, so we noticed that this question satisfies all the criteria that we noted for the use of the word integral. Namely, there is a domain. There is an integrand. I can chop this domain up into little pieces. When I chop the domain up into little pieces, the quantity in question associated to each piece, namely in this case the volume under the graph sitting over that piece, when you add up over all of the pieces, you get the total quantity that we're actually interested in. Namely, the total volume of this thing is the sum of the volumes of these, French fries that you get when you slice it up like that. So that's nice. Furthermore, notice that on each little piece, as per one of our other requirements, our estimate of the quantity in question, the volume here, is the value of our integrand, height, this being a graph, therefore f, times the size of our little piece of our domain. And the size, well, we have to reinterpret the idea of size here. This is a two-dimensional domain. In two-dimensional domain, size means area. So area of that little sub-rectangle times height of the French fry gives me the volume inside of that French fry. And when I add up over all the French fries, I get the volume of the original potato. Everybody on board with this? So this really fits in structurally with all of the applications that we saw in Calc 1 classes, Calc 1, Calc 2 classes. Only difference being that this is with a two-dimensional domain, so adapted appropriately. Okay. All right, so we were in the process of discussing details, and I want to remind everyone that there's this breakdown here for, if you have an interval on the x-axis, like so, then you can break it down in the following way. When you do these, when you slice it up, you call those endpoints, x1, x2, etc. Just for the sake of consistency, you can rename A as x0. Therefore, then B as xn. Notice that in the ith subinterval, the right endpoint is x sub I. Right. Okay. The width of one of these subintervals, as long as you're slicing up into n equally sized pieces, the width is b minus a over n. So here's a lot of sort of reproduction of old news right here. So I hope all of this looks familiar. By the way, if this is not familiar, if you're exposure to Riemann sums previously was maybe a little weak. This would be a great thing for us to talk about in office hours. Come on in and we'll talk through where these formulas come from in maybe a little greater detail, and also how specifically you can use this to quantify Riemann sums for specific values of n and how to get real precise with it. Okay. All right, so now our sort of further problem is, here we have a two-dimensional domain rectangle. We're chopping up this two-dimensional domain, but we're chopping it up two different ways. On the one hand, we're making slices like this. Right? On the other hand, we also have to slice like this. I mean, it's not good enough to have pieces that are long and skinny. Long and skinny slices is not acceptable. Let me real quick talk about why long and skinny slices are not acceptable. One of my requirements is that on each one of the pieces, as I slice, I need the value of the integrand to be approximately constant. I'm being deliberately ambiguous, deliberately sloppy. Approximately constant on the slice. And now I just appeal to your intuition about functions of two variables. Just because I slice this really thin, well, that means the function's not going to vary as you move left and right, because you can't move very far left and right. But you've got a long way that you can go up and down. And the value, why could you expect the function to have approximately the same value here as it does way up here? The answer is, and usually you can't. Right? If the constraint that you would like to have on your integrand is that it, let's say, be continuous, nice requirement in the sense that the vast majority of functions satisfy, that will be then our condition is not satisfied by this long skinny slice. So we have to double slice. We have to slice everything up into little sub-rectangles like that. And now I've got to quantify these little sub-rectangles. Where are these sub-rectangles? How wide is it? How tall is it? What's the coordinates of its bottom left corner? Etc. So no big deal as it turns out. Notice that when you slice this rectangle, you also effectively, at the same time, are slicing the interval from A to B that defines its, if you will, its shadow down here on the x-axis. And we know what happens if you take the interval from A to B, if you slice up the interval from A to B. So the x-coordinates relevant to this little sub-rectangle is going to be the same x-coordinates as the x-coordinates that we've already dealt with down here. Okay. Likewise, when we slice the other way, when we slice horizontally, notice that, in effect, at the same time, we are slicing up this interval on the y-axis, from C to D, what I'm calling C to D, which are, if you will, the defining y-coordinates, or you might say the projection, the shadow of our rectangle over onto the y-axis. Right? So slicing up on the rectangle horizontally, it's just another slicing of an interval. Now, minor detail, that interval is sitting up instead of lying down, right? But it's got a starting point, an ending point, and we're slicing it into n equal slices. The structure of the argument there is going to be a lot like what we just got through looking at, and no surprise then with the familiar results down here. Delta y is, instead of b minus a over n, it's d minus c over n. And y sub j is, it's going to look like a lot like the formula for x sub I, but we're starting in c instead of a, and we're going to the jth piece instead of the ith piece, and each one has with delta y instead of delta x. So, I mean, the structure of the argument here is pretty much the same, just different details appropriate to this context of being the interval from C to D. Okay. All right, and so there's the details, and what we've got it down to now is this little sub-rectangle here d sub ij, which now let's just blow it up for visualization purposes. If this is the ith slot, if you will, on the x-axis, then that coordinate is x sub I. This coordinate is x sub I minus 1. If this is, if you will, the jth slot on the y-axis, well, then this is y sub j minus 1 to y sub j. And each one, I now know the coordinates of all four of these corners, and I know the width, and I know the height. And I can tell you exactly where that subrectangle is. By the way, you'll notice here that for notational convenience, I'm labeling this thing as d sub I comma j. You need two indices to define which subrectangle you're talking about, because that subrectangle corresponds to, well, which of the n slices are you in, if you will, along the x-axis, and likewise then a second index j to tell you which of the n slices are you sitting inside of along the y-axis. So I for the x-axis, j for the y-axis. How are we doing? Is everybody with me? Any questions? Okay. Alrighty. So here's our strategy then for how we're going to compute the volume. On each little piece, height times area. Height times the area of the base, if you will. And notice this fits the structure of our previous Riemann sums. Value of an integrand. The integrand, because it's the function of this graph we're looking at, therefore it gives us the height. And we're multiplying by the size of our new piece of our sliced up piece of the domain, size now being area instead of length. Okay. We've already argued that when you then add that up over all the pieces, we should get, round off error is acknowledged, disappear in the limit, but when you add up all those pieces, you should get the total volume in question. Okay, now one little remaining detail. Let's just go ahead and get precise with it. What do we mean about the size of this piece d sub ij? Well, size is height times width. The width is delta x. The height is delta y. So I think this is a pretty easy appeal that the area that we're looking for there, that area is delta x times delta y, and I'm going to call that delta a just for notational convenience. It's the amount of, there's a total area, but this is the amount of that total area that's in that little piece. Okay. Now, just a reminder, this is a different kind of a summation than what we've seen previously. In our previous summations, I goes from 1 to n. That's it. I goes from 1 to n. You got an interval, you chop it up to n pieces, you add up as I go from 1 to n. So notice that this is different in the sense that there are sort of, if you will, n different slices in that direction, but for each of which then, on each of which there are a bunch of slices going vertically. Right? So for each of the n slices down here, you have in fact n slices sitting above it. So grand total, you have n squared. Different terms in this summation. So, it's a little bit weird to think about. We're accustomed to considering, when you're looking at Riemann sums, what happens if n equals 10? Well, if n equals 10, you have to add up 10 different terms. Not anymore. If n equals 10 now, you have 100 different terms in this Riemann sum to add up. So that doesn't sound like any fun. It's looking like it's going to be, an awkward expression to evaluate, but let's be optimistic that a better way will present itself. And it will soon, today. Yeah. Okay. Before we get into how to compute these things, though, let's get the definition written down on the page. We've already seen a success in this expression. This expression that I have circled here has been a way that we can precisely write down and quantify how would we go about computing the volume under the graph of some surface. I don't want to do it that way, but nevertheless, this would get the job done, however inconvenient it might be. Now, I'm going to appeal to your sense of analogy, and hopefully your trust in me, that this is actually going to be useful in a lot more places than that, right? Just like Riemann sums in a Cop 1 class. Yeah, you compute the area under a graph, and that's nice and all, right? But the more importantly, you can compute the amount of work that it takes to perform a task, or the number of bacteria in a petri dish, or oh my gosh, I mean, y'all saw lots and lots of different applications of integrals, aka Riemann sums, in Calc 1 classes. The area under the graph is, convenient, nice, but not the point. Right? The same thing's going to happen here. Again, the analogy suggests it, and I'm about to show you a bunch of such applications momentarily. Okay, so point is, this expression, I believe we have enough cause at this point to believe that this should be important. Right? We motivated it from the point of view of one particular application, volume under a graph, but because this is going to be useful for other things, I want to give it a name and a notation now, and the name is that this is a double integral. I'll talk more about why we call it a double integral a little bit later. It's a double integral. We use this notation to represent a double integral. It's just two integral symbols right next to each other. We'll talk more about why that choice is made in a few minutes. A double integral of this function f, whatever is the function that is the what we call the integrand, the thing that you multiply by size in the summand. That function is called the integrand. So we say we are doing a double integral of f. And then I've got to tell you what is the domain. The domain is what defines what are these coordinates and what is the area of this slice. All that stuff comes from what the domain is. We indicate the domain with a little subscript down there. This is just kind of for convenience. I mean, what's our alternative? If we want to say, look, I've got this rectangle and I want to do a double integral over that rectangle. Well, this rectangle it's got 4 separate corners. What am I going to list all the corners? That would get inconvenient pretty fast. So it's a nice, convenient shorthand. Define your domain elsewhere. Give it a name. Let's call it D. Let's make the subscript our notation there. So this is clunky. Okay. So double integral of this function f over that domain D. Written like this. And you give me a function, you give me a domain, I can identify all the participants in this Riemann sum expression precisely using formulas on the previous page. This becomes a well-defined, hard to compute, but well-defined thing, and that hard to compute value is what we mean by doubling. Let me take another breath, give you all a chance to ask a question if anybody has one. Okay. Alrighty. Okay. So another notational alternative I'll mention real quick. This dA here, given that dA is intended to be suggestive of delta A, given that delta A is delta X times delta Y, that kind of suggests that maybe we could write dA as dx times dy, and I guess you can. The thing I want to emphasize, though, that it's better to think of this as a single thing. It's better to think of this as an area. Fundamentally, we are multiplying the integrand times an area, and there's kind of not much to be bought at this stage by rewriting it as dx dy. It's more to write down. It takes up more space on the page. In this context, we only need these things, dx and dy, as part of this product, dx dy. So I think it just makes a lot more sense to write it as dA. So, anyway, that's a thought for your consideration. It's not wrong if you write dx dy, but I like it better as dA. Okay, and there is another related idea that we will talk about later, another different perspective on the whole dx dy thing that we will get to later today. Okay. One last notational little quickie. This business about using two integral symbols, a lot of books, especially advanced, so higher level books. If you take Math 531, for example, right? Very likely they would just write this as with a single integral symbol. They would write it like this. The idea being that, well, I said right there that the domain is D. D is given. It's a rectangle. It's two-dimensional. Of course we're chopping up the little pieces of area. Of course I meant double integral. Why would you make me draw the separate integral symbol again? The context makes it clear this has to be a summation over a two-dimensional region. And it's just kind of no point in drawing the second integral symbol. Now, I'm not going to use this notation in this book, in this course. But I just wanted y'all to be heads up about that. I will continue to use this, if only as kind of a nudge reminder, kind of a visual cue that, hey, don't forget, this is a double integral. It's arguably, though, the third reminder, right? Because this pretty clearly says size, and this pretty clearly says, two-dimensional domain. Okay. All right. Okay, so what can we do with these things? Let's consider the following application. Let's suppose we are looking at a sheet of metal. This is a two-dimensional version of the mass of a rod example, right, that we all saw in Calc 1 classes. Instead of a one-dimensional non-constant density, here we have a two-dimensional thing, a sheet, where the density is not constant. The metal alloy has got more iron in some spots and more aluminum in other spots. So here's our sheet of metal. And, again, maybe it's more dense over here and less dense over there. How would you compute the total mass? A couple of things to observe about this problem. This domain can be chopped up into little pieces. The thing that we are looking for, mass, is an accumulating quantity. I remind you, not everything in the physical world is an accumulating quantity. Center of mass, right? Not an accumulating. Perimeter. The perimeter of this rectangle is not the sum of the perimeters of the little rectangles that you slice it up into, right? So very non-trivially, but critically, I observe that mass has this accumulation feature that, if I take this sheet of metal, if I were to chop it up into a bunch of little pieces, the masses of those little pieces would add up to the mass of the original thing. And finally, notice that mass is a product. It's a product of some function, soon to be called my integrand, times the size of that piece. Again, one of the critical requirements if you're going to talk about an integral, the quantity in question on each piece has to be some factor, some function times the size of that piece. Mass does have that feature. Mass is what times area? Well, it's mass per unit area, and that's density. By the way, just a real quick, this term density, I'm going to use density in several different senses appropriate to the context. So if we're talking about a three-dimensional region, which we will pretty soon, not right now, but if you're talking about a three-dimensional region, density means mass per unit volume. Okay. If we're talking about a two-dimensional region, density means mass per unit area. There is no volume. What's the volume of which you speak, right? That doesn't make any sense at all. So mass per unit size, where size is appropriate to the context. And remember, when we were looking at rod problems, density was mass per unit length. Okay. For whatever it's worth, by the way, this is not that mysterious of a concept. If you were to go to the hardware store and buy some chain, Right? This is not a sophisticated activity, right? This is, you walk right up to it, pull the chain off the spool, and say, I want to buy this much, right? That chain, when they describe that chain, they will describe, how much it weighs based on the length, mass per unit length. Because what else would you do? I mean, it doesn't make sense to talk about, the length is the appropriate, that's what you need to know about a chain, is how long is it? And the metal that makes it up and what the mass per unit volume is inside of that metal, who cares, right? I need to know, I know the more chain I buy, the more it's going to weigh. And I need to know how much does it weigh per unit length. And right there on the side of the spool, it should tell you how much does this weigh per unit length. So anyway, these appropriate interpretations of density, I think make a lot of sense, and it's very important that we interpret them appropriately in each context. Okay. So this question, mass distributed over an area, has got all the earmarks of a question that can be dealt with one of our new double integrals. And so we can write down the answer accordingly. Mass is an accumulating quantity. If I chop it up into little pieces, the original mass is the sum of the individual pieces of mass. There's that accumulation feature. Each little piece of mass relates to area. There is an integrand that I can multiply by area to compute that little piece of mass. And notice that I then get a Riemann sum. Is everybody happy with that? And Riemann sums, of course, are integrals. Okay. So now here's the thing. This is an integral. The Riemann sums, what's an integral? And I know I'm going to rewrite, as soon as I get a Riemann sum that is an integral, I'm going to rewrite it as an integral. So I'm going to rewrite that like that, and there's my integral my double integral that I'm going to use to express the answer to this question. But since we're going to use this notation eventually, there is a kind of an accepted shorthand. Let's call it. Floppiness would be another alternative, but let's call it a shorthand. That since we're going to use the notation of integral eventually, then it is implicit what I mean if I use it a little bit prematurely over here. So, for example, in the same sense that this is kind of just taking the place of that. I mean, this integral says a summation over a limit. Well, then how about I go ahead and use the convenience in advance there. Right? And likewise, we use d whatever as an eventually, and when we get to the actual Riemann sum that we rewrite as an actual integral, that delta effectively is shorthanded with a d. So how about we go ahead and give ourselves that luxury in advance and write it like that? Yeah.
Is there any reason why there isn't like an x sub I and a y sub I and just x and y?
Oh, no, you're right. There should be xi and a yj in there. Yeah, I'm just being shorthanding. Just shorthanding. Yeah. Good catch. Okay, so the shorthand that I want to encourage y'all to use, everybody uses this. It's fine, no problem. Is instead of developing the Riemann sum in Riemann sum notation, and then only once you get to a full-on actual integral Riemann sum do you rewrite it as an integral. Instead of that, go ahead and do it like that. Right? It's implicit that when you write this, what you really mean is that. It's fine. Okay. What is important is that when you write stuff down like this, let there be no ambiguity in your mind as to exactly what that means. That means this. Right? And don't make the mistake of thinking that somehow there's an m-axis or something. Because there isn't. This is shorthand for that Riemann sum that's in the process of making its way toward this Riemann sum, namely this integral. So this is just shorthand for a developing Riemann sum. Is that cool? Anybody happy? Okay. All right. Okay. Here's another question. Suppose you want to compute the population of Colorado, and our alternatives at this point are Colorado and Wyoming, right? Because all we know how to do is to compute. We have a definition of double integrals over rectangles, and those are the only two pure rectangular states. I think, pretty sure. Correct me if I'm wrong on that. But anyway, so we're going to pick Colorado arbitrarily. And let's compute that total population with the given being that I know the population density function. Population, number of people per unit area in Colorado. And maybe I have an analytic function describing this, or more likely I just have data on this that allows me to simulate a function. Okay. Real quick reminder. Let's reinterpret, appropriate to this example, what do we mean by density? And to be silly, when we say that population density, we do not mean the physical density of the population, right? So you've got to interpret density in a slightly different way here. This density is a very flexible word. It can mean a lot of different things depending on your context. We're going to make substantially more flexible interpretations of the word density later on in the course. In other words, in like a week. So even more generally than we previously talked about, mass per unit area as opposed to mass per unit volume. The further extension is going to be, hey, it doesn't have to be mass. It could be some sort of accumulating quantity, like the number of people. Right? If you have a great big region of area, the number of people total over the whole region is the sum of the numbers of people in each little piece of the area. If you slice up the area into little pieces. So any accumulating quantity that's distributed over any sort of a size, be it an area or a volume, right? If you wanted to talk about the density of, I don't know, there's probably like microbes floating around in the air in here. The population density of microbes in the air in this room wouldn't be quoted in population per unit area. It would be quoted in population per unit volume of air. Okay. So general notion of density, stuff per unit size, appropriate to the context. How y'all feel about that? All right? All right. Okay, so all that being said, I'm going to use the same picture here. This is no longer a sheet of metal. This is now the state of Colorado. Right? And now, instead of looking at mass, I'm looking at population. And if I were to slice up Colorado into a bunch of little pieces, the total population is the sum of the little populations in the pieces. And in each little piece, how would I compute the population in that little square? There, I would say, well, the population there is population density times area. People per unit area times area gives me people. Okay. And so, here's that development. Now, a little micro detail to worry about here. Notice that the population density, we know the population density function is called F in units of thousands of people per square mile. Right? So F being 1 means that there's 1,000 people per square mile. Right? So don't forget to pay attention to the units, and as appropriate to that, we have to multiply by an extra factor of 1,000. So said differently, this is the actual number of people per square mile. And notice that again we have people per unit area times area. That gives us people. We are adding up people to get total people. How about it? Everybody on board? Okay. All right. Okay, here's a non-trivially different example. I didn't draw this picture as well as I should have, but here's a tube. There's water flowing in this tube. or pipe, what have you. Okay. And I'm given the velocity at any location. So, for example, at this point here, I'm told what is the velocity of the water at that point. Now, keep in mind, velocity is given in units of distance per unit time. Okay. What I want to know is, given that being the case, well, here's the edge of the pipe over here. And by the way, the flaw in this drawing is I didn't give it a rectangular cross-section. I made it kind of a round pipe. I need it to be a rectangular pipe because we're going to make an integral. Our only domains at this point are rectangles. So anyway, let's pretend we have a rectangular pipe. Not the weirdest thing in the world. Over here at the end of the pipe, I want to know volume per unit time. How much water is gushing out of the end of this pipe? Right, so throughput, flow rate, total flow rate. And that's in units of volume per unit time. Okay. Everybody on board? Okay. So here's the way we're going to approach this problem. The first thing I'm going to do is say, well, with my region, and again, I apologize for the bad picture, but this rectangular cross section, I can chop up that rectangular cross section into little pieces. Right, on each little piece of that cross section, I could ask how much water per unit time is flowing through that piece, just that piece. And I appeal to your sense of physics, how the world works. If the cross section were divided up into little sub-rectangles, the amount of water per unit time flowing through each individual rectangle, if I were to add up over all the individual rectangles, it would give me the total amount of water flowing through the pipe. Okay. By the way, just so you know, when water flows through a pipe, naively we sort of expect that as well. It's just all moving at the same speed, but it isn't. Water is moving slower near the edges and faster in the middle. That's how it works. So this is a non-trivial problem. There's a temptation to say, just come on, whatever the velocity is, just tell me what the velocity is. We'll multiply by the area, and boom, there you go. But velocity, hard problem. Okay, so we're going to look at each individual piece. We'll start off by looking at this little piece of area right there. On that little piece of area, let's ask how much flow rate is there. What's the total volume per unit time flowing through that little rectangle? Volume per unit time. Here it is, volume per unit time. I can see the volume explicitly in this picture in a given amount of time, delta T. Here's the volume that I'm interested in. So I want to know how to compute that volume. That will be our numerator. In that amount of time T, this distance here, well, distance is velocity times time. The area is already known. The area is delta A. Right? And so grand total, I have, width is velocity times time times area, delta A. That gives me the total volume that passes through that little area in a given amount of time, delta T. And then, again, flow rate is volume per unit time. So you notice that the delta T's cancel. And what I'm left with after a non-trivial little, geometric physical argument, you might even say unexpectedly, what we have is that the flow rate is this expression here, and notice it is a function times area. It was not obvious that this was going to be the case. Right? But as is required in order to fingers crossed, hopefully be able to use a double integral to answer this question. I need, on each piece, for the quantity in question, to be some function times area. Yay, worked out. So, conveniently, I now have a domain, I have an integrand, and per that argument there, on each little piece, the total flow rate through each little piece is velocity times area. Adding up over all the pieces, I get what is recognizably, conveniently, a Riemann sum, namely a double integral. And then, of course, we remember, oh yeah, that's true. Instead of going around, notationally awkward like that, I could just instead write this. Totally fine. Okay. Everybody okay? Okay, so we have now seen a bunch of examples of this expression being useful. Right? So 15 minutes ago when we first wrote this down, at the time, this had been useful for exactly one application: volume under a graph of a surface. This is arguably, not that much motivation. But now we've seen that it computes not only volumes, but it will compute masses if you know density. It will compute populations if you know how population is distributed. It computes flow rates through tubes if you know the velocity to where you are in the tube. And then I ask you to let your imaginations run wild. It's endless. There's lots and lots of different kinds of applications that break down structurally in this form that are Riemann sums and therefore double integrals. Okay. Next question we're going to address. We found that there's a bunch of questions that morally look like this. We've developed a notation. We've developed a terminology. And sad to say, notation and terminology alone do not help us compute things. Right? The looming dark cloud over this whole conversation is we still don't know how to compute this. Yeah? See what I'm saying? Right, let's go back to single variable calculus. We wrote down this expression, and that's all well and good to have a notation and a terminology representing Riemann sums, but are we going to actually crank these things out as this? I mean, by the way, when y'all took Calc 1, did they make you do that a couple times? Actually crank out Riemann sums? No, they made me crank out a few explicit Riemann sums directly, right? As written. In other words, write down the formulas for all these things. Do the summation as a function of n, and then followed by taking a limit as n goes to infinity. And it's doable sometimes, but really only sometimes. It's a real non-trivial calculation. So back to Calc 1. How did we actually get the job done? How did we actually compute these things? Oh, we have fundamental theorem of calculus, right? For sure. I mean, no doubt. So structurally, the way you solve calculus problems in a Calc 1 class is you write your application as a Riemann sum, aka an integral, and then you compute it a totally different way. The fundamental theorem of calculus is awesome. F of B minus F of A, that's that whole business. Okay, so do we have, I ask rhetorically, for our double integral thing, do we have a fundamental theorem of calculus kind of thing that's going to let us just, I don't want to go this way. This way looks really hard and really high. Whoa, yikes, right? Is there a fast and easy way to compute double integral? And the answer is kind of, but not in the way that you're hoping. That's a good news, bad news situation. So anyway, here we are. So not exactly. So not quite. What we can do is we can rewrite double integrals in terms of single variable integrals. So we're not going to have a single formula for a double integral, but we are going to be able to rewrite double integrals in terms of single variable integrals, and then we're going to say, and we know how to compute single variable integrals. Okay, so the way to get at this, there's different points of view on how to connect a double integral to a single variable integral. The way I'm going to do it is not rigorous. This is not intended to be rigorous. This is deliberately sloppy, because a rigorous presentation of this idea is it's got sticky wickets, and I don't really want to deal with the sticky wickets for one thing. The other thing is, in this Math 212 class, the other thing is that I want y'all to have a geometric sense. I want you to have, even non-rigorous though it is, I think there's a lot of value in seeing the picture of why something should be true, independent of some sort of rigorous argument as to why it actually is true. Right? So I think there's a lot of value in that. And y'all are mostly engineers. I think the intuition and the motivation are more valuable for you. So here's where I'm going to come at this. I'm going to revisit a question that we already know the answer to. Correction, a question that we already know an answer to, namely volume under a surface. It's a double integral. We already know that, right? But let's take a different point of view on it. So here it is, volume under a surface. Right? We already know about the French fries. Right? You chop up the area at the bottom into little rectangles, view the volumes of the French fries, add them up. That's the double integral approach. But let's not do that. Let's take a different approach. And the approach I want to take is an approach that might seem familiar to those of you who have seen, let me do a little hand waving. In Calc 1 classes, you computed, or maybe Calc 2, the volume that you get when you revolve an area around an axis. Do y'all remember those? So you take, here's your x-axis, and you take some curve. But when you take that curve and rotate it around the x-axis, now you've got a solid three-dimensional thing. And the idea was that solid three-dimensional thing that when you take a cross-section of it, when you take a slice, that little slice has a volume. That's going to be the cross-sectional area, which is like pi r squared or whatever, times the thickness. Do y'all remember that whole thing? Okay. This is a standard application in Calc, probably in Calc 2, I guess. Single variable calculus. Okay, so a solid has slices with a cross-sectional area and a thickness giving little volumes that add up to the total volume. That's the takeaway there. So here's what I'm going to do. Even though the question that we're looking at here, this volume under a surface, it's not a rotation. This is not the cross sections are not circles. I can nevertheless argue that, a dead end though this may appear to be, if I were to be able to figure out what this cross sectional area is, and if I were to multiply that cross-sectional area times this thickness here, delta x, the area of that cross-section times the width, namely the thickness, a of x times delta x would give me the volume of this odd little slice of bread or whatever, right? And again, geometric appeal, the total volume of this strange loaf is the sum of the volumes of the individual slices of bread. Right? All right. So that's what this says. Here, the total volume is the sum of the little pieces of volume, which are areas times thicknesses. And I say dead end because, again, we're modeling off of what we did back in a Calc 2 class where we had a volume of revolution, and the volume of revolution, that cross-sectional area was a disk. We know the formula for the area of a disk. Do I know the formula for an area if it's not a barnyard type common geometric figure. And well, not really, right? This A of x, that's that area there. It's not a disk, and it's not a variation on a disk, and it's not a triangle, and it's not a rectangle, and it's not a. So this formula here seems to be a dead end, but it's actually not. What we have to do is just have faith, press on, and we're actually going to be able to figure out what this area is. And the way we're going to figure out what this area is we're going to look at our picture, and we're going to reimagine this picture. Okay, so there's our picture, right? We're looking for forget about the delta x for the moment. Let's just look just at the cross-sectional area. That cross-sectional area, here it is again. Here's the big point, the key idea. That cross-sectional area is the area under a curve, right? There's a curve, and we're looking for the area under it. So we're looking for the area under a curve. And that, of course, is a visual, an audio knee-jerk, right? With area under a curve, right? Whoa, hey, I know how to compute the area under a curve. We've done a lot of that. So if you want to compute the area under a curve, what we need to know is what is height as you move along. And as you move along here, as you go from C to D, as this y coordinate here, that describes where you are underneath that cross-section curve. As that y goes from C to D, your height is given by that formula right there. So we've got some fixed value of x. In other words, it's at a given value of x that we want to compute the cross-sectional area. For that value of x, we're trying to compute a of x, this cross-sectional area. Given that x, this point has x coordinate, which is x, and y is going to range from C to D, and height is f. How we doing? Everybody good? Okay. And hey, no problem if you. How did we compute areas under curves way back when? Well, area under a curve is an integral. It's an integral of whatever the height is, which we have, right? Height times, the differential, what is the little width down here? Well, which direction? Well, we're looking at moving along the y-axis. This height is being multiplied by width in the form of that right there. That is width along the y-axis. That's this, we're looking at this interval from C to D. We're chopping up this interval from C to D into little pieces. It's delta y, literally. Right. And the area then, that area is f of x comma y times delta y. I'm going to take a pause on this for a moment as well. Everybody on board? Now we're kind of deep in the weeds at this point, right? It's like, what were we doing again? Right? Why are we computing that area? So let me just remind you. Let's go back and see what our pictures are saying. The first thing that we were doing was arguing that the total volume was the sum of the volumes of the slices of bread, and that those volumes were areas times widths delta x. Delta x, because they're little slices of the integral from a to b. This little thickness here is b minus a over a, and that is delta x. So we were looking at an integral of a of x dx. Here it is. We were looking at an integral of a of x dx. A of x, this area that we're interested in, that a of x is our integrand. But that a of x, we see and so this a of x is the sum of these terms here. That a of x is itself an integral. Here it is. A of x is integral of f times dy. Let me go back down to the picture. This cross-sectional area, what we're going to be adding up, these little slices of area, f of x comma y, delta y. Everybody okay? So let's combine everything together now. We're looking at an integral of a of x. A of x itself is an integral, which is weird. All combined together, we get this. Volume is an integral of a of x. A of x itself is an integral of f of x comma y dy. So altogether, the volume is an integral of, so it's an integral, let me highlight. It's an integral of an integral. Isn't that weird? Probably never seen an integral inside of another integral before. It's, I mean, it gets us there. It's a way to approach the problem. I'll point out, by the way, I think this is a lot less sort of simple and elegant than our double integral strategy. Our double integral strategy says, look, you've got an area, chop it up into little pieces. On each piece, height times base. Right? It's a simple little story. Here we've got cross sections in different directions, and dx for the first part of the discussion, and dy for the second part, and there's a lot of sort of, keeping track of what stage of the calculation are you in. But there is something really, really, really nice about this result, and that is that this is a single variable integral, and I know how to compute single variable integrals. We have a fundamental theorem of calculus for single variable integrals. The resulting of which gives me the integrand for that outside integral, which is a single variable integral, and I know how to compute single variable integrals. They are computed with also, again, fundamental theorem of calculus. So this, slightly weird though it is directly computable easily. That's the appeal. Now, let's talk about terminology. My discussion for this is I like to call these nested integrals, because I think nested is just pretty natural, right? We have something sitting inside of something else. So I think that makes sense, calling them nested integrals. The more common terminology is to call these iterated integrals. And I get that. It's okay. We've got this f, and we're doing an integral, and then we're going to do another integral. It's like you're iterating, if you will, the process of integrating. What I don't like about this term iterated integral is it makes it sound like you're doing the same thing twice, and you're really not. This inside integral, what I like to call the inside integral, is dy for one thing, from c to d for another thing. The outside integral is not. It's dx. And it's from a to b. It's really a very different process. This is not the repetition of the same process twice. So anyway, it rubbed my fur backwards a little bit to say iterated integral, because I just feel like that term iterated is just a little too strong. Anyway. So you're going to hear me say nested integral, but you'll also hear me say iterated integral, and outside of Math 212, you're going to hear iterated integral more often, much more often. So, okay, all right. Now I do want to talk about what's going on with these integrals a little bit more. Let's talk about the inside integral in particular. What is going on there? How do I interpret what's on the inside here? What does this mean? Well, don't forget, the whole reason we wrote down that inside integral is because it computes cross-sectional area for it. So when that inside integral, I want y'all to think of it as a computation of this area of this cross-section for a given value of x. So notice all of that cross-sectional area is for that given value of x. And let me write this down here. It is, in fact, a of x that we're computing. And I just want to do this in a different color. Its area is a function of x. So it's only for a fixed value of x that we can even talk about that inside integral. So in practice then, when you're looking at one of these iterated integrals, nested integrals, for the purposes of the inside integral, you have to treat x like a constant. It was good news, by the way. Otherwise, we'd be pretty freaked out. Like, oh, I've got two variables in here. How do you even do an integral if you have two variables in a single variable integral? That's not something we've ever seen before, right? So, good news. That's an illusion. For the purposes of this inside integral, there are not two variables. That x is a constant. Right here, visible in the picture. For that whole inside integral, x does not change. You treat it like a constant because it is a constant. Everybody on board? Okay. Now that's for the inside integral. Now for the outside integral, of course, everything changes. For the outside integral, x is absolutely a variable. X ranges from a to b. For the purposes of the outside integral, x ranges from a to b. X is the variable. X is what's changing. We're looking at little widths, delta x. So x is to be treated as a variable once you get to the outside integral. And question comes up, what about y? How do you treat y for the purposes of the outside integral? The answer there is there's no y's. The y's will be gone. Notice there was no y's in this discussion. Right? That total volume for any given value of x, there is a cross-sectional area that is well defined. If you give me an x, I will call its cross-sectional area a of x. I multiply by delta x. Didn't say y anywhere in that whole conversation. And then when you get to the algebraically, what does that look like? Once you have evaluated this thing here. Once you have cranked out, the antiderivative and stuff, keep in mind, the very last step is to plug in these numbers, c and d, in place of y. That's the whole f of b. Well, it's going to be capital F of d minus capital F of c, right? And all the y's will have c's and d's stuck into them, and there will be no variables y remaining. So let's see an example how this actually cranks out in practice. So let's compute the volume under that surface. Notice that this surface is a graph. It's a graph of that function. Right? Quick callback to older stuff. What's important about this surface is what it is a graph of. Because I need to know how to interpret heights. Don't rewrite this as x squared plus y squared minus z and talk about how, this is a level set of this other function. That's not, that function x squared plus y squared minus z does not tell me height. I need height is z. I'm looking for how to interpret this as a graph. We're looking at a graph of this function. Okay, so that's what I'm going to take a double integral of. That's what I'm going to take an iterated integral of. So here we go. By the way, notice my domain being this here. But I should talk about this notation. This notation, it's a few pages back. I'll go back to it. Almost there. Here we go. Yeah, here we go. This notation the first interval listed there is telling you the shadow of our rectangle on the x-axis, and the second interval listed after the cross is telling you the shadow of our rectangle on the y-axis. All right, so rectangles conveniently are described by, well, what's the corresponding range of values of x and what's the corresponding range of values of y. So that's the notation that indicates that. Okay. Okay, so here we have x ranges from 0 to 1 and y ranges from 0 to 1. And so in doing our iterated integral, the x integral goes from 0 to 1. Correspondingly, the y integral goes from 0 to 1. And of course, height is our integrand, as discussed in the previous application. So that's what goes on the inside there. Everybody on board? Okay. So now let's start computing. When we look at this integral, this iterated integral here, there is a temptation to want to go outside in. I'm not really sure. It's just kind of the very first thing you see, I suppose, is the integral symbol for the outside integral. You can't do the outside integral first, because the outside integral, its integrand, is something I have not yet worked out. Right? So unavoidably, you have to go inside out. You have to start with that inside integral. The inside integral, I can see the integrand. There it is. And so I can proceed with, going through the usual process. Don't forget, as previously discussed, for the inside integral, x is a constant. Right? For this inside integral, you can see right there, y is the variable. We're going over values of y from 0 to 1 for the purpose of identifying a cross-sectional area for a given fixed value of x. So when you're doing these inside integrals, I cannot emphasize enough, make sure to remember that x is a constant. And notice how that works out in the integration. There's a strong temptation, a huge mistake, strong temptation for students to say, oh, well, the integral of x squared is 1/3 x cubed. Not here it isn't. Right? Here, x is a constant, so x squared is a constant, and the integral of a constant is constant times that variable. This being a dy integral, we get x squared times y. Everybody good? But one of the more common mistakes that beginners make on multiple integration. So now, on the other hand, this next term we have y squared. Y is the variable. So the integral of y squared, just as you might expect, 1/3 y cubed, exactly as you'd like to write down. And then, plug in as usual. So y goes from 0 to 1. So the values you plug in are y equals 0, y equals 1. Before I plug in those numbers, a suggestion. You don't have to do this, but I think it's a really good idea. Notice that I didn't just put 0 and 1 here. I put y equals 0 and y equals 1. Because the thing is, otherwise, there is in this line no other visual indication of which variable should you be plugging in these values for. Right, so very importantly, you're plugging in these values 0 and 1 for y. And it is so easy without this little visual cue to just plug in zeros and ones for just every variable, just stick it in for x's and y's and just the whole thing. Strong temptation. So my little this is a superstition on my part, you might say, or a recognition of my own sort of I'm somewhat prone to inadvertent, careless, mindless errors, and so you write y equals 0 to y equals 1. It's a little bit of help there. So you're going to plug in those values 0 and 1 into, for example, there and there, which makes this turn into that, right? And then plugging in y equals 0 there and there turns this into that. And so notice we have our familiar, capital F of B minus capital F of A. It's just a fundamental theorem of calculus. Okay. Is that a hand? Yeah, what's up?
This is a pretty obvious question, but
Yeah,
the half parenthetical is just to denote separation.
Yeah, no, so this, great question. So this, he's asking about, I think you're asking about that little half bracket there.
And
No?
the left.
Yeah, sure. That's sort of, that's a recognition that this expression here, what I need to do to compute this integral is I need to plug in these two values and subtract. It is a shorthand for what, otherwise I would have to write literally capital F of B minus capital F of A. And it's just more to write down. It's just easier. Yeah. No. Okay. All right. Now notice, what do we have left? Well, we've got a bunch of algebra. This has got to be simplified, blah, 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 blah. And here's what it simplifies to. It simplifies down to that. Here, let me color code better. This inside integral then has now simplified to that. And now what do we do? How do we do this outside integral? What are the landmines? What do I do with the y's in here? I know to treat x as a variable because it's a dx integral, and so x is ranging from 0 to 1. But what about the y's? Notice there are no y's. We plugged in for them. The y's were a dummy variable for the inside integral that's not there anymore. So of course the y's are all gone. This is a good old, plain old Math 111L single variable integral like y'all have done a billion of in the past, and its evaluation is just a matter of cranking it out. So easy antiderivative, you notice. Plug in these values 0 and 1, and there's your answer. Anybody on board? Okay. All right. I have lost track of time, and we are now past break time. So let's go ahead and we'll take a break here. Let's see here. It's 11:13. See y'all 11:23. Okay. See you then.